Tonight we float beside a darkness so complete that it seems less like an object and more like a missing piece of reality. There are stars all around you. Vast rivers of them. Blue stars, white stars, ancient red giants glowing softly in the distance. Yet ahead, occupying the center of your vision, is something that shines with no light at all. A supermassive black hole. You drift silently toward it. At first, it doesn't look particularly dramatic. The darkness itself is almost perfectly round, a black circle cut into the fabric of the universe. But around it swirls a glowing disk of gas hotter than many stars. Light bends strangely around the edge. Distant galaxies appear stretched and warped into impossible shapes. You feel as if you are approaching a cosmic magic trick. Only this trick is real. And somewhere beyond that dark boundary lies a mystery that scientists still cannot solve. What happens to everything that falls in? Not simply the matter. Not simply the energy. But the information. The story. The record that something ever existed at all. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're here, leave a comment telling everyone your location and local time. It's always fascinating to see where in the world fellow night travelers are listening from. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You continue drifting. The black hole grows larger. A surprising thing happens. The closer you get, the more beautiful it becomes. This seems unfair somehow. The universe has taken one of its most dangerous objects and wrapped it in elegance. Streams of glowing gas orbit at enormous speeds. Some of that gas circles thousands of times before disappearing forever. Friction heats it to incredible temperatures. Radiation pours outward across space. The established scientific fact is simple. Black holes themselves emit no light. Their gravity is so strong that once something passes a boundary called the event horizon, not even light can escape. Yet the regions around black holes can become some of the brightest places in the universe. It's a bit like discovering that the world's darkest cave hosts the most extravagant fireworks show. The universe enjoys irony. You watch a star orbiting far away. The star appears ordinary enough, but its path reveals something astonishing. Astronomers have spent decades observing stars circling the supermassive black hole at the center of our galaxy. Those stars move so quickly that only an immense invisible mass can explain their motion. No telescope directly photographs the black hole itself in the traditional sense. Instead, scientists observe its influence. Like footprints in fresh snow. Like leaves swirling around an unseen whirlwind. Like noticing your snacks disappearing and realizing someone else lives in the house. Or perhaps a raccoon. Cosmic mysteries and raccoons both have a habit of leaving evidence while avoiding direct observation. Ahead of you, space-time itself begins to distort. That phrase, space-time, sounds abstract when spoken in a classroom. Out here it feels tangible. You imagine space not as emptiness but as a vast structure. A cosmic landscape. A four-dimensional stage where every event unfolds. The black hole changes that stage. It bends it, warps it, twists it. Even time becomes affected. If you could somehow hover near the event horizon and then return home, you might discover that more time had passed for distant observers than for you. Time itself would have flowed differently. This is not science fiction. It emerges directly from Einstein's theory of general relativity. Gravity is not merely a force pulling objects together. It is the curvature of spacetime. And black holes represent that idea pushed to an extreme. As you drift closer, another question emerges. Where did this thing come from? Some black holes form when massive stars die. After exhausting their nuclear fuel, they collapse under their own gravity. The stellar core shrinks. Matter compresses. Eventually, a black hole may remain. But the one before you is far larger. Millions of times more massive than the Sun. Possibly billions. Scientists know such giants exist throughout the universe. What remains uncertain is exactly how some of them became so enormous so quickly. In the early universe, less than 1 billion years after the Big Bang, supermassive black holes already existed. That is the surprising observation. They appear almost too early, too large, too mature. It's as though you opened a history book to the first chapter and discovered skyscrapers already standing. Something about the timeline feels incomplete. Perhaps giant clouds of gas collapsed directly into black holes. Perhaps smaller black holes merged repeatedly. Perhaps some unknown process operated in the universe's youth. The evidence points toward possibilities. The answer remains elusive. You continue approaching. The event horizon now dominates your view. This boundary is often misunderstood. It is not a physical wall, not a glowing membrane, not a giant cosmic force field. If you crossed it, you might not notice anything unusual in that exact moment. No alarm sounds. No cosmic security guard appears with paperwork. No enormous sign flashes. Warning: reality ends here. Instead, the event horizon marks a limit. A point beyond which return becomes impossible. Every path forward leads deeper inward. Every future points toward the center. And that center hides another mystery. According to current equations, deep within a black hole lies something called a singularity, a region where density becomes infinite and our known laws of physics break down. Whenever physicists encounter infinities like this, alarm bells start ringing. Not literal bells, unfortunately. Physics conferences would be much more exciting. But mathematical infinities often signal that a theory has reached its limits. General relativity describes gravity extraordinarily well. Quantum mechanics describes the microscopic world extraordinarily well. Yet inside black holes, these two great frameworks refuse to cooperate. The universe seems to be withholding a piece of the puzzle. And that puzzle may be connected to one of the deepest questions ever asked. Can information truly disappear? Imagine writing every detail of your life into a book. Every memory, every thought, every conversation, every dream. Now imagine dropping that book into the black hole ahead. What happens to the information it contains? At first glance, the answer seems obvious. The book is gone. Problem solved. Except physics does not like that answer. Many laws suggest information should never be completely destroyed. Yet black holes seem to threaten exactly that. Somewhere inside this darkness lies a contradiction between our best descriptions of reality. A contradiction so profound that generations of scientists have struggled with it. And tonight, as you drift closer to the edge of the unknown, that mystery waits patiently ahead. The stars continue shining. The glowing disk circles endlessly. The black shadow remains silent. You are still outside the horizon, still looking in, still wondering. And the universe, as it often does, offers no immediate answer. Only another question. The black hole hangs before you like a hole punched through existence itself. You remain at a safe distance for now, suspended in the darkness while the glowing disk slowly turns around the shadowed center. The question that followed you here still lingers. What truly happens beyond the horizon? Before you move closer, though, it helps to understand how humanity discovered these strange objects in the first place. Because the story of black holes begins long before anyone believed they could be real. You look outward, away from the darkness for a moment. The stars spread across the cosmos in every direction. For most of human history, those stars seemed eternal, fixed, reliable, mysterious, certainly, but not dangerous. Ancient civilizations watched them move across the sky. They built calendars around them. They navigated oceans beneath them. They told stories about them. The sky appeared orderly. Yet hidden within that order was a secret. Gravity. The invisible force connecting every object in the universe. An established scientific fact is that gravity governs the motion of planets, stars, galaxies, and even light itself. Without gravity, the cosmos as we know it would simply not exist. For centuries, gravity seemed straightforward enough. Objects fall. Planets orbit. Apples become famous. One particular apple achieved a career level most fruit can only dream about. Then, in the late 18th century, an intriguing idea emerged. What if gravity became so strong that light itself could not escape? At the time, nobody knew light's true nature. Yet some thinkers began wondering whether an extremely massive object might trap light forever. The idea was strange, interesting, mostly forgotten. After all, such an object sounded absurd. Then the 20th century arrived. And everything changed. You watch the stars while imagining another journey. One taken not through space, but through ideas. In 1915, Einstein introduced general relativity. Suddenly gravity was no longer simply a force acting across empty space. Instead, mass and energy shaped the geometry of spacetime itself. The universe became something flexible. Dynamic, curved. Picture a heavy bowling ball resting on a stretched sheet. Smaller objects roll toward it because the surface bends. The analogy is imperfect, but useful. Mass tells spacetime how to curve. Curved spacetime tells matter how to move. And once Einstein's equations appeared, something unexpected emerged from the mathematics. The equations seemed to permit regions where gravity collapsed inward without limit, places from which nothing could escape, even light. At first, many physicists viewed these solutions with suspicion. Surely nature would never allow something so extreme. Surely some hidden mechanism would intervene. Surely the universe had better things to do than create cosmic trapdoors. The universe, unfortunately, rarely consults us before making decisions. As decades passed, evidence accumulated. Astronomers observed stars exploding. They studied dense stellar remnants. They discovered neutron stars, objects so compact that a teaspoon of their material would outweigh mountains. And if nature could create neutron stars, perhaps it could continue compressing matter even further. The possibility became harder to dismiss. You continue watching the rotating gas around the black hole. The disk glows with fierce energy. Some regions shine brighter than entire galaxies. This is one of the surprising observations of modern astronomy. The brightest objects in the universe are often powered by black holes. Not because black holes shine, because matter falling toward them releases tremendous energy. Imagine water rushing toward a waterfall. Now imagine the waterfall is millions of times deeper than anything on Earth. The infalling gas accelerates enormously. It heats up. It collides. It radiates. The result can outshine billions of stars. In the middle remains darkness, a silent center driving the spectacle. By the 1960s and 1970s, evidence for black holes grew stronger. Radio telescopes revealed strange sources of energy. X-ray observatories detected invisible companions pulling material from nearby stars. Galaxies displayed violent activity in their cores. Everywhere astronomers looked, gravity seemed to be doing something extraordinary. The universe was beginning to reveal its hidden engines. And then came another realization. Black holes were not rare curiosities. They appeared to be everywhere. Small ones, large ones, perhaps intermediate ones, and gigantic supermassive monsters occupying galactic centers, including the one at the center of your imagined journey. You drift slightly closer. The warped light around the black hole becomes easier to see. A galaxy behind it appears stretched into a luminous arc. This effect is called gravitational lensing. Light follows the curvature of spacetime. When enormous masses intervene, the path of light bends. You are witnessing gravity acting on light itself. Not metaphorically. Literally. A black hole becomes a kind of cosmic lens, an invisible sculptor reshaping the appearance of the universe. This leads to a fascinating observation. If you could somehow position yourself nearby, you might see multiple distorted images of the same distant object. Reality itself would seem folded. The cosmos would appear less like a static picture and more like a hall of mirrors designed by geometry. Yet even these remarkable effects are not the deepest mystery. The deeper mystery lies inside, or perhaps beyond, or perhaps in a place our current theories cannot properly describe. You think again about the singularity. Mathematics predicts it. Physics struggles with it. Whenever scientists calculate conditions near the center of a black hole, the numbers become troublesome. Density grows without bound. Curvature becomes infinite. Known equations stop behaving sensibly. This unresolved mystery remains one of the greatest challenges in theoretical physics. Most researchers suspect the singularity described by current equations is not the final story. Instead, it may indicate missing knowledge. Something deeper. Something not yet understood. Perhaps a future theory of quantum gravity will reveal what truly happens. Perhaps spacetime has a microscopic structure. Perhaps black holes contain phenomena we have not even imagined. At the moment, nobody knows. That uncertainty matters. Because black holes sit at the intersection of two enormously successful theories. General relativity governs the large-scale universe. Quantum mechanics governs the microscopic one. Both theories work extraordinarily well. Yet inside black holes, they seem incompatible. It's as though you possess two maps. Each map is accurate. Each successfully guides travelers through vast territories. But when the maps overlap, the roads no longer match. Somewhere in that mismatch lies a missing truth. You stare into the darkness again. The shadow seems almost peaceful now. Not threatening. Not violent. Just patient. Waiting. Around it swirl clues collected across generations of human curiosity. Observations. Equations. Hypotheses. Questions. The closer science approaches the mystery, the larger the mystery appears. That is one of the strange gifts of discovery. Every answer expands the frontier. Every solved puzzle reveals deeper puzzles waiting behind it. The black hole before you is not merely an object. It is a doorway into unfinished science, a place where knowledge ends and uncertainty begins. And soon you will drift closer still, toward the boundary where time itself starts behaving in ways that challenge common sense, toward the horizon, toward the edge of the known universe's most persistent mystery. The black hole no longer feels distant. It fills a huge portion of the sky now, a dark sphere wrapped in ribbons of light. The glowing disk around it spins endlessly, bright enough to illuminate the surrounding darkness. Stars behind it appear bent and distorted, as though the universe itself has become soft and flexible. You continue drifting closer, not falling yet, just approaching, carefully. The mystery remains ahead, but something else begins to happen. You start noticing that space itself no longer behaves the way you expect. This is where black holes become especially strange. Most objects in the universe are things that exist within space. Planets move through space. Stars burn within space. Galaxies drift across space. Black holes seem different. In a sense, they reshape space itself. An established scientific fact is that a black hole's gravity comes not from some mysterious force unique to black holes, but from mass concentrated into an extraordinarily small region. The same gravity that keeps Earth orbiting the Sun operates here. The difference is intensity, and intensity changes everything. Imagine standing on a calm hillside. Now imagine standing beside a cliff. Gravity is present in both places, yet one environment feels entirely different. A black hole is gravity transformed from a familiar background actor into the main character. The closer you drift, the more space-time curves. If you could release a beam of light beside you, its path would no longer travel perfectly straight. Instead, gravity would guide it along the warped geometry surrounding the black hole. This is difficult to picture because everyday life trains you to think of space as empty. Black holes reveal that space is not merely emptiness. It possesses structure, geometry, shape. You gaze outward. A distant star appears duplicated, then stretched, then curved into a thin luminous arc. This surprising observation is not imaginary. Astronomers regularly observe gravitational lensing across the universe. Entire galaxies can act as lenses, bending the light of more distant galaxies behind them. Sometimes a single object appears multiple times. Sometimes rings of light emerge. Sometimes giant invisible masses reveal themselves solely through their gravitational effects. In fact, some of the strongest evidence for unseen cosmic matter comes from these distortions. But that mystery waits farther ahead. For now, your attention returns to the black hole. Its gravity dominates everything nearby. Yet another odd thing becomes apparent. If you watched someone else falling toward the event horizon while you remained far away, their movement would appear increasingly strange. Their clock would seem to slow. Their motions would become sluggish. Their signals would arrive farther apart. To your eyes, they would appear frozen near the horizon. Not because they stopped, because time itself behaves differently. This is one of the most astonishing consequences of relativity. Time is not universal. It does not flow identically everywhere. Near powerful gravitational fields, time slows relative to distant observers. The stronger the gravity, the greater the effect. You can almost feel this concept taking shape around you. The black hole is not simply pulling on objects. It is reshaping the passage of time. The universe becomes less like a giant clock and more like an ever-changing landscape of clocks moving at different rates. If that sounds unsettling, you're in excellent company. Many physicists felt the same way. Some still do. The universe apparently decided that time should be flexible. Nobody asked for this. Reality simply delivered the update. You drift onward. The horizon grows larger. And another thought emerges. What exactly is the event horizon? People often imagine it as a physical surface. A wall, a shell, a barrier. But it is none of those things. The event horizon is better understood as a boundary in the future. A point beyond which all possible paths lead inward. Once crossed, escape becomes impossible not because engines fail, but because every available direction through spacetime leads deeper toward the center. It is less like hitting a wall and more like reaching the top of a waterfall. Beyond a certain point, every route carries you downstream. This realization makes the black hole feel even stranger. The event horizon is not made of matter. It is made of geometry, a feature of spacetime itself. You watch glowing gas spiral toward that invisible limit. Some material circles for years, some for centuries, some eventually plunges inward, never returning, never sending another message outward. The horizon keeps its secrets, and those secrets become even more troubling when quantum physics enters the story. For now, though, you remain in the realm of relativity. You imagine releasing two clocks. One stays far from the black hole. One moves closer. When reunited, they disagree. This is not speculation. Experiments throughout modern physics have repeatedly confirmed that time dilation is real. Precise atomic clocks flown aboard aircraft measure tiny differences. Satellites account for relativistic effects every day. Without those corrections, systems like GPS would gradually fail. Black holes simply push these effects to extraordinary extremes. The closer you move, the stranger time becomes. Yet perhaps the strangest thing of all is how natural this appears. The black hole does not look angry. It does not look violent. It simply exists. A consequence of physical law. The universe creates stars. Stars evolve. Some collapse. Gravity does the rest. There is a kind of elegance in that simplicity. And yet simplicity often hides deeper mysteries. The unresolved mystery here is profound. General relativity predicts the behavior of spacetime around black holes with astonishing accuracy. Observations repeatedly confirm its predictions. But near the center, the theory breaks down. The equations point toward a singularity, a place where our understanding ends. Scientists strongly suspect that a more complete theory must exist. One that unites gravity and quantum mechanics. One that explains what truly happens when matter reaches extreme densities. One that reveals whether singularities are real or merely signs that our current mathematics is incomplete. No such theory has yet been confirmed. That missing piece remains one of the greatest unsolved problems in science. You continue drifting. The black hole's shadow now occupies nearly everything ahead. Around its edge, light performs impossible-looking loops. Some photons orbit briefly before escaping. Others circle multiple times. Some vanish forever. Imagine following a single photon on its journey. Born inside a distant star. Traveling across millions of years. Crossing galaxies. Navigating clusters. Only to arrive here and become trapped by gravity. Its voyage ends at the threshold of darkness. A tiny particle of light swallowed by spacetime itself. And yet even that description may be incomplete. Because later in your journey, another mystery will emerge. A mystery suggesting black holes may not be perfectly black after all. A mystery that forced physicists to rethink everything they thought they understood. For now, though, you remain suspended between certainty and uncertainty. You know that gravity bends space. You know that time slows near immense mass. You know that black holes exist. The evidence is overwhelming. But beyond those facts lies a question still unanswered. What truly waits inside? The closer you approach, the more that question seems to expand. Like the shadow before you. Like the universe itself. Like a doorway that grows larger every time you think you've reached it. The horizon is close now. Not close in the ordinary sense. Distances around a supermassive black hole can be deceptive. You could fit entire solar systems into regions that, from here, appear almost compact. Yet something feels different. The boundary that has hovered at the edge of every thought since this journey began now dominates your attention. The event horizon. The point of no return. The place where one of science's greatest mysteries begins. You drift toward it slowly. The glowing disk continues its endless rotation behind you. Stars still sparkle in the distance. The universe remains beautiful, calm, and strangely indifferent. Nothing announces that you are approaching one of the most extreme environments in existence. No warning sirens. No cosmic fence. No giant sign reading, beyond this point. Physics may become complicated. Which is probably for the best. Space already contains enough surprises without bureaucratic signage. You continue forward. And to understand what happens next, you must perform a thought experiment. Thought experiments have long been among science's most useful tools. Before humanity could build spacecraft, physicists traveled through imagination. Before telescopes revealed distant realities, ideas often arrived first. So imagine that you are not merely observing. Imagine you are falling, not struggling, not resisting, just surrendering to gravity. An established scientific fact is that if you crossed the event horizon of a sufficiently large supermassive black hole, you might not immediately notice anything unusual at the exact moment of crossing. This surprises many people. Popular culture often portrays the horizon as a dramatic barrier. Reality appears stranger. According to general relativity, crossing the horizon itself could feel uneventful. No flash. No impact. No sudden shockwave. You simply continue moving. And yet everything has changed. Because escape is no longer possible. Not due to mechanical limitations. Not because some force prevents movement outward. But because spacetime has been warped so severely that every future path leads inward. This idea can feel slippery. Imagine standing on Earth. You can walk north, south, east, west. Multiple futures remain available. Inside the horizon, the geometry becomes radically different. Moving toward the center becomes as unavoidable as moving toward tomorrow. The singularity lies ahead in much the same way that next Tuesday lies ahead. Not as a destination you choose, but as part of the structure of reality. You continue falling. At least in imagination. Outside observers see something entirely different. This is where relativity becomes especially fascinating. Someone watching from far away would never actually see you cross the horizon. Instead, you would appear to slow. Signals from you would arrive more gradually. Light leaving your spacecraft would become increasingly redshifted. Your image would dim, fade, and seem almost frozen at the edge. To them, crossing appears to take forever. To you, it happens normally. Both descriptions emerge from the mathematics. Both are valid within their respective perspectives. The universe once again refuses to behave according to everyday intuition. Time itself has become part of the puzzle. You glance outward. The stars behind you no longer look familiar. The sky appears distorted. Light from regions once hidden now bends into view. The black hole acts as a giant gravitational lens, wrapping portions of the cosmos around your field of vision. The effect would be breathtaking and deeply disorienting. You might see the same star in multiple locations. Different regions of the universe overlap visually. Space begins folding information toward you. The view becomes less like looking through a window and more like staring into a kaleidoscope designed by Einstein. Yet another mystery emerges. Suppose you carry a book. A simple book. Nothing extraordinary. Just pages filled with words. Memories. Stories. Information. And suppose that book falls with you. What happens to the information inside? At first, the answer seems straightforward. The book falls inward. Problem solved. But physics dislikes easy answers when black holes are involved. Information is not merely knowledge. In physics, information describes the precise state of a system, the arrangement of particles, their properties, their relationships. Many physical laws suggest that information should never truly vanish. The universe appears remarkably protective of it, and yet black holes seem capable of destroying it. That contradiction sits at the center of a profound unresolved mystery. You continue imagining the descent. The horizon now lies behind you. No turning back. Ahead waits the singularity predicted by general relativity. Or perhaps something else entirely. Nobody knows. This uncertainty is important. Scientists often speak confidently about black holes because many aspects are supported by overwhelming evidence. We know black holes exist. We know stars orbit them. We know they shape galaxies. We know gravity behaves around them exactly as predicted. But the interior remains hidden. Observations cannot directly reveal what occurs beyond the horizon. The universe keeps that region private. And because information cannot escape, testing ideas becomes extraordinarily difficult. Black holes are nature's most effective secret keepers. The deeper you imagine traveling, the more theoretical the landscape becomes. General relativity predicts continued collapse. Quantum mechanics begins demanding attention. Neither theory willingly yields. Both work astonishingly well elsewhere. Yet here, at the edge of understanding, tensions emerge. It is as though two master musicians are playing different versions of the same symphony. Each performance sounds beautiful on its own. Together, something doesn't quite align. Physicists have spent decades searching for harmony. They have not found it yet. The surprising observation is that black holes, despite being among the most mysterious objects in existence, can often be described by only a few measurable properties. Mass, charge, spin. That's largely it. The enormous complexity of everything that falls in seems to disappear from the outside description. A star, a planet, a cloud of gas, a library, a collection of socks that vanished mysteriously during laundry. From the outside, much of that detail appears lost. This simplicity is elegant and deeply unsettling. Because where did all the complexity go? Did it survive somehow? Was it encoded elsewhere? Was it transformed into something we do not yet understand? The mystery grows larger the closer you look. You continue falling through imagination alone. The singularity remains ahead like a question mark hidden inside darkness. Perhaps it exists exactly as the equations predict. Perhaps quantum effects prevent its formation. Perhaps space-time changes character entirely. Perhaps new dimensions become relevant. Perhaps reality itself possesses structures we have not yet discovered. At present, these possibilities remain speculative. Observations have not settled the matter. The horizon conceals the answer. And that concealment creates one of science's most frustrating situations. You know something extraordinary is happening. You know your theories are incomplete. You know a deeper explanation must exist. Yet the region where the answer likely resides is inaccessible. A locked room in the architecture of the cosmos. You think back to the beginning of the journey. The distant black circle. The first glimpse of warped starlight. The simple question. What lies beyond? Now, standing at least conceptually beyond the horizon, the question feels even larger. Because the mystery is no longer merely about what exists inside a black hole. It is about whether the universe itself obeys rules we do not yet understand. And soon, another discovery will make the puzzle even stranger. A discovery suggesting that black holes may not remain black forever. A whisper from quantum physics. A faint glow from the edge of darkness. One that transformed a difficult mystery into one of the deepest paradoxes in modern science. The horizon has disappeared behind you now. At least in imagination. Outside, the universe continues expanding. Stars continue shining. Galaxies continue their slow dance across cosmic time. Somewhere, planets circle their suns. Somewhere, intelligent beings may be asking questions remarkably similar to yours. Yet here, deep within the thought experiment, you carry a puzzle that refuses to loosen its grip. The puzzle of information. The puzzle that transformed black holes from strange astronomical objects into one of the greatest unsolved problems in physics. You continue drifting inward. Not toward answers. Toward deeper questions. At first glance, information seems like an odd thing to worry about. After all, information sounds abstract. Words on a page. Bits in a computer. Memories in a mind. But in physics, information is something more fundamental. It describes the exact arrangement of reality. The precise state of every particle. Its position. Its momentum. Its quantum properties. The detailed recipe that makes the universe what it is. An established scientific fact is that quantum mechanics, our most successful theory of the microscopic world, strongly suggests that information cannot simply be destroyed. It can be transformed, hidden, scrambled, scattered, but not erased from existence. This principle lies at the heart of modern physics, and black holes appear to challenge it. Imagine once more that book falling inward. Perhaps it contains every detail of a civilization, every language, every history, every work of art, every scientific discovery, the entire cultural memory of a world. Now imagine the book crossing the event horizon. From the outside, all those details seem gone. The black hole remains. The information does not appear accessible. Where did it go? This question may sound philosophical. It is actually mathematical. And the equations become uncomfortable remarkably quickly. You continue your descent through darkness. The singularity remains hidden ahead. Meanwhile, outside the black hole, Physicists in the 20th century were uncovering another astonishing piece of the puzzle. A surprising observation emerged not from telescopes, but from theory. Black holes might not be completely black. This idea arrived through the work of the brilliant physicist Stephen Hawking. In the 1970s, Hawking combined ideas from quantum mechanics and relativity in a way nobody had fully explored before. The result was startling. According to his calculations, black holes should emit a tiny amount of radiation. Today we call it Hawking radiation. The concept is subtle. Quantum physics describes empty space as anything but empty. Even the vacuum seethes with activity. Tiny quantum fluctuations constantly appear and disappear. Particles emerge. Particles vanish. The vacuum resembles a restless ocean rather than a featureless void. Near a black hole's event horizon, these fluctuations create unexpected consequences. Without diving into the mathematics, the result is that the black hole can gradually lose energy. Over immense timescales, it slowly evaporates. The larger the black hole, the slower this process occurs. For a supermassive black hole, evaporation would require a duration so vast that it dwarfs the current age of the universe. Yet the implication remains. Black holes are not eternal. This revelation changed everything. Because now the information puzzle became far more severe. Before Hawking's discovery, one could imagine information remaining trapped inside forever. Perhaps inaccessible, but still present. Hawking radiation complicated that possibility. Suppose the black hole eventually evaporates completely. What happens to the information then? If the radiation contains no record of what fell in, information appears destroyed. Quantum mechanics objects. Strongly. The contradiction became known as the black hole information paradox, and for decades it has remained one of the deepest mysteries in theoretical physics. You float in darkness, contemplating the scale of the problem. This is not merely a disagreement between scientists. It is a conflict between two foundational pillars of modern physics. General relativity describes black holes. Quantum mechanics governs information. Both theories work extraordinarily well, yet together they seem to produce an impossible situation. Somewhere something is missing. Imagine assembling a puzzle with thousands of pieces. Everything fits beautifully, until the final section. Then suddenly the remaining pieces belong to a different puzzle entirely. That is roughly how physicists feel about black holes. The closer they get to completion, the more obvious the mismatch becomes. Over the years, numerous ideas have been proposed. Some suggest information escapes within Hawking radiation itself. Not lost, merely encoded in extraordinarily subtle ways. Others propose that information remains on the event horizon. Still others suggest entirely new structures emerge near black holes. Possibilities include holographic descriptions of spacetime, quantum entanglement networks, or phenomena not yet fully understood. What matters is that no universally accepted solution has emerged. The mystery persists. You continue imagining the inward journey. The darkness feels immense now. Yet paradoxically, the mystery feels larger still. Black holes possess a remarkable ability to transform local questions into cosmic ones. A question about a collapsing star becomes a question about information. A question about information becomes a question about quantum mechanics. A question about quantum mechanics becomes a question about reality itself. Every layer reveals another. And another, and another. The universe behaves like an endless series of doors. Open one. Find 10 more behind it. There is another curious aspect to this story. Black holes seem extraordinarily simple from the outside. Physicists sometimes summarize this through the phrase, "Black holes have no hair." The expression does not mean black holes require cosmic shampoo. It means that most details about the objects that form them appear absent from their external description. Mass, charge, spin. Those remain. Much else appears erased. A collapsing star and an enormous collection of textbooks could produce black holes that look nearly identical from the outside. The rich complexity seems hidden, or perhaps encoded in ways not yet understood. That uncertainty remains unresolved. The deeper scientists investigate, the stranger the situation becomes. Information appears simultaneously hidden and preserved, lost and not lost, gone and not gone. The language itself begins struggling to keep pace. You think again about the stars far beyond the horizon, about galaxies, about the long history of human curiosity. For centuries, mysteries often yielded when enough observations accumulated. Black holes are different. Their most important secrets reside beyond direct observation. The challenge is not merely gathering more data. It is developing entirely new frameworks capable of reconciling gravity and quantum physics. Somewhere in that future theory may lie the answer, or perhaps an even deeper mystery waiting behind it. The darkness ahead remains silent. The singularity remains unseen. The paradox remains unresolved. And as remarkable as all this already seems, the puzzle is about to expand beyond black holes themselves. Because once scientists began confronting these contradictions, they discovered something unsettling. Black holes might not be the only hidden mystery shaping the cosmos. In fact, most of the universe may consist of things we still do not understand at all. The paradox lingers like an echo. You carry it with you as the imagined descent continues. Information seems unable to disappear. Black holes seem capable of making it disappear. Quantum mechanics insists on one thing. General relativity appears to insist on another. Neither theory has shown any intention of backing down. And so the mystery deepens. You now find yourself not merely asking what happens inside a black hole, but questioning whether the universe itself has hidden rules waiting to be discovered. The darkness around you feels larger than before. Not physically, conceptually, because every answer uncovered so far has generated even bigger questions. This is where Hawking's whisper becomes impossible to ignore. The idea that black holes evaporate is strange enough on its own. A black hole seems like the ultimate consumer, a cosmic one-way door. The last thing anyone expected was that it might slowly leak away into space. Yet according to Hawking's calculations, that is exactly what should happen. Tiny amounts of radiation emerge. Tiny amounts of mass disappear. Over unimaginable spans of time, the black hole shrinks. An established scientific fact is that Hawking radiation remains one of the most important theoretical predictions connecting quantum mechanics and gravity. Although the radiation is far too faint to detect directly from astrophysical black holes with current technology, the prediction is taken extremely seriously because it emerges naturally from established physics. And that creates a remarkable situation. The very phenomenon that may eventually destroy a black hole is also the phenomenon that creates the information paradox. You picture the giant black hole before you. Its mass equals millions or billions of suns. Its gravity governs entire regions of a galaxy. Yet even this monster is not truly permanent. Given enough time, it too would fade. Not tomorrow. Not next year. Not even after trillions of years. Far beyond that. The timescales involved are almost absurd. If the current age of the universe were compressed into a single second, the evaporation of a supermassive black hole would still lie so far in the future that ordinary language struggles to describe it. Cosmic patience reaches extraordinary levels. The universe is apparently in no hurry. You float quietly beside this realization. And then another question appears. If black holes eventually vanish, what remains? The radiation, the energy, the information? Nobody knows for certain. Over the decades, physicists have proposed increasingly fascinating possibilities. One idea suggests that the information is somehow encoded within Hawking radiation itself, not destroyed, not lost, merely scrambled into forms so complex that reconstructing the original state becomes practically impossible. Imagine taking a beautifully organized library and shredding every page. The information technically still exists. Every letter remains present. But reassembling the books becomes unimaginably difficult. Perhaps black holes do something similar on a cosmic scale. Another possibility emerged from a surprising direction. The mathematics of black holes began hinting at connections between gravity and information itself. Some researchers proposed that the universe may operate in ways resembling a hologram. Not a hologram in the science fiction sense of glowing projections floating in midair. A deeper concept. A mathematical relationship suggesting that information describing a volume of space might somehow be encoded on its boundary. The idea sounds almost impossible. Yet it has become one of the most influential concepts in theoretical physics. The surprising observation is that calculations involving black holes repeatedly point toward unexpected links between geometry and information, space and knowledge, gravity and computation, reality and description. Concepts once considered separate now appear strangely intertwined. The deeper scientists look, the more interconnected everything becomes. You glance outward through imagination. Beyond the black hole lies the broader universe. Galaxies, clusters, immense filaments of matter stretching across billions of light years. At first, these structures seem unrelated to the information paradox. Yet subtle connections are beginning to emerge. Because black holes may not merely be astronomical objects. They may be clues, hints pointing toward a deeper understanding of reality itself. Some physicists even suspect that solving the black hole paradox could reveal how spacetime emerges in the first place. That possibility is astonishing. Imagine discovering that the mystery of a collapsing star ultimately explains the nature of space itself. The universe has a habit of connecting distant questions. Like threads woven through a tapestry. Pull one. An entirely different region begins to move. Yet despite decades of effort, no final answer has appeared. This remains the unresolved mystery at the heart of the journey. Does information escape? Does it remain hidden? Does quantum gravity transform the problem entirely? Is there some deeper principle not yet discovered? The evidence remains incomplete. The debate continues. And black holes continue guarding their secrets. You drift in silence for a while. The darkness no longer feels threatening. Instead, it feels ancient, patient, a monument to unanswered questions. Humanity has learned extraordinary things. We have measured the expansion of the universe, detected gravitational waves, photographed the shadows of black holes, observed planets orbiting distant stars. Yet here, at the intersection of gravity and quantum mechanics, uncertainty remains. And uncertainty is not failure. It is the frontier. Every major scientific breakthrough once existed as a mystery that seemed impossible. Black holes themselves were once dismissed as mathematical curiosities. Now they sit at the center of modern astrophysics. What appears mysterious today may become foundational tomorrow, or it may reveal even deeper mysteries waiting beneath. The black hole remains silent. Its shadow still dominates the cosmic landscape, but your attention is beginning to shift outward, because the paradox surrounding black holes is not the only great puzzle in existence. Far beyond this darkness lies a revelation even more startling. A discovery showing that black holes are not the only things we struggle to understand. In fact, when astronomers measured the universe carefully, they uncovered something extraordinary. Most of the cosmos appears to be missing, not hidden behind an event horizon, missing from our understanding altogether. And that mystery may be even larger than the black hole itself. The black hole remains behind you now, a vast shadow lingering at the edge of thought. Its mysteries have not disappeared. The information paradox remains unresolved. The event horizon still conceals whatever lies beyond. The singularity remains hidden behind equations that no longer behave the way physicists would like. Yet as your attention drifts outward into the wider cosmos, something surprising becomes clear. The black hole is not the only mystery. It may not even be the biggest one. You leave the immediate vicinity of the horizon and begin looking across the universe itself. Galaxies spread in every direction. Some are elegant spirals. Some are giant ellipticals. Some appear distorted by collisions that began millions of years before humans first walked the earth. The universe feels immense, structured, orderly, at least at first glance. Then you notice something strange. The numbers do not add up. This realization began taking shape during the 20th century. Astronomers carefully measured how galaxies rotate. According to ordinary expectations, stars near a galaxy's center should orbit rapidly, while stars farther away should move more slowly. This is similar to how planets in our solar system behave. Mercury races around the Sun. Neptune moves much more leisurely. Gravity weakens with distance. The pattern seems straightforward, but galaxies refuse to cooperate. An established scientific fact is that stars at the outer edges of many galaxies move far faster than visible matter alone can explain. The observations have been repeated countless times. Again and again, the same result appears. Something unseen is exerting gravitational influence. Something massive. Something invisible. Astronomers named it dark matter. The name sounds dramatic. It also reveals a certain honesty. Dark matter is called dark matter largely because we do not know exactly what it is. Scientists sometimes receive criticism for naming things this way. But in fairness, mysterious invisible stuff that appears to exist but refuses to explain itself would have been difficult to fit into textbooks. Dark matter is concise. You gaze across a distant galaxy. Its stars orbit within an enormous halo of unseen mass. The surprising observation is that ordinary matter, the stars, planets, gas clouds, dust, and everything visible, appears to account for only a small fraction of the universe's total contents. Everything familiar. Everything you have ever touched. Every mountain. Every ocean, every living thing, every black hole formed from ordinary matter. Together they represent only a minority of the cosmos. The realization is humbling. Imagine reading a 1,000-page book and discovering that you understand only 50 pages. The remaining 950 pages remain largely unread. That is roughly where modern cosmology finds itself. The universe has revealed enough to demonstrate how much remains hidden. You continue traveling outward through imagination. Clusters of galaxies come into view. Some contain hundreds, others thousands. Immense gravitational cities scattered across the cosmos. When astronomers map these structures, dark matter appears everywhere. Its influence shapes galaxies, guides cosmic evolution, acts as an invisible framework supporting the large-scale structure of the universe. And yet nobody has directly identified its nature. Scientists have proposed many possibilities. New particles, exotic forms of matter, entire families of previously unknown components of reality. Experiments continue. Observatories search. Detectors wait. So far, no definitive answer has emerged. The mystery remains. The black hole suddenly feels less lonely. It has company now. Another enormous question standing beside it. But the universe is not finished. Not even close. Because dark matter represents only part of the puzzle. As astronomers continued measuring the cosmos, they discovered something even stranger. The universe is expanding. That part was already known. Galaxies generally move away from one another as space itself expands. This discovery transformed 20th-century astronomy. Yet later observations revealed something unexpected. The expansion is accelerating. Not slowing down. Accelerating. This was astonishing. Gravity attracts. Matter pulls matter together. Most scientists expected cosmic expansion to gradually decelerate over time. Instead, observations suggested the opposite. The universe appeared to be speeding up, as though some invisible influence were pushing space apart. This surprising observation earned recognition as one of the most important discoveries in modern cosmology. To explain it, scientists introduced another term: dark energy. Once again, the name is wonderfully direct. Dark energy means more or less. Something appears to be causing this effect, and we do not yet know what it is. Dark energy seems to permeate space itself. Unlike dark matter, which clumps gravitationally around galaxies, dark energy appears remarkably uniform. It acts across the universe, quietly, relentlessly, driving accelerated expansion. And here comes the truly staggering part. Dark matter dominates ordinary matter. Dark energy dominates almost everything. Together they constitute the overwhelming majority of the universe. The stars you admire, the galaxies you explore, the black holes that inspired tonight's journey, all belong to the comparatively small fraction we understand best. The cosmic balance sheet is deeply unsettling. Most of reality remains mysterious. You pause among the galaxies. The scale of this realization settles over you. The black hole mystery once seemed enormous. Now it appears embedded within an even larger landscape of uncertainty. The unresolved mystery is profound. What is dark matter? What is dark energy? Are they separate phenomena? Are they connected? Could they somehow relate to gravity itself? Might they even connect to the puzzles surrounding black holes and information? At present, nobody knows. Theoretical models exist. Observational evidence continues accumulating. But the final explanation remains elusive. You drift onward through immense cosmic structures. Filaments of galaxies stretch across unimaginable distances. Gigantic voids separate them. The universe resembles a web, a network spanning billions of light years. And everywhere you look, invisible influences shape what you see. The cosmos begins feeling less like a completed picture and more like a partially illuminated map. Small regions are brightly understood. Vast territories remain in shadow. In some ways, this resembles the black hole itself. You can study the surroundings, measure the effects, observe the consequences. Yet the deepest reality remains hidden. Perhaps that similarity is meaningful. Perhaps it is coincidence. Scientists remain cautious. Evidence comes first. Speculation follows. Still, the pattern is difficult to ignore. Every time humanity uncovers a new layer of understanding, another hidden layer appears beneath it. The universe seems determined to remain at least partly mysterious. And the farther you travel, the stranger that mystery becomes. Because beyond dark matter and dark energy lie even more radical possibilities. Ideas involving wormholes, white holes, inflation, multiple universes, concepts that push scientific imagination toward its limits. Some remain plausible. Some may be wrong. All attempt to illuminate regions where certainty fades. And ahead, the frontier grows darker still. The universe stretches around you like an endless ocean of unanswered questions. Far behind, the black hole still waits in memory, a dark circle that began this journey. Around it gathered mysteries of gravity, information, and time. Beyond it emerged dark matter and dark energy, hidden influences shaping nearly everything we observe. And now the horizon of uncertainty expands again. Because once scientists reached the edge of what observations clearly revealed, they encountered a new landscape. A territory where evidence remains incomplete, where mathematics sometimes runs ahead of direct confirmation, where possibilities multiply faster than answers. This is the frontier, not pseudoscience, not fantasy, but the outer boundary of serious scientific speculation, a place where researchers cautiously ask questions that would have sounded impossible a century ago. You drift through darkness between galaxies. The stars seem fewer here, the distances greater, the silence deeper. And in that silence, another question emerges. Could black holes be connected to tunnels through spacetime itself? The idea sounds like science fiction, yet it arises naturally from certain solutions to Einstein's equations. These hypothetical tunnels are known as wormholes. An established scientific fact is that the mathematics of general relativity allows solutions resembling bridges connecting distant regions of spacetime. Whether such structures actually exist in nature remains unknown. The equations permit them. Observations have not confirmed them. That distinction matters. Throughout this part of the journey, evidence and speculation must remain separate. Scientists have learned the importance of that lesson many times. Nature often surprises us. Sometimes by being stranger than expected. Sometimes by being simpler. You imagine a wormhole. One entrance near a distant galaxy. Another billions of light years away. Instead of crossing immense cosmic distances through ordinary space, a traveler might pass through the tunnel and emerge elsewhere. The concept is elegant and extremely problematic. Many theoretical analyses suggest wormholes would be unstable. They might collapse instantly. Keeping one open could require exotic conditions not known to occur naturally. For now, wormholes remain possibilities rather than discoveries. Still, the fact that such possibilities emerge from our best theories is fascinating. Reality appears far more flexible than common sense would suggest. The black hole returns briefly to your thoughts. Some researchers have wondered whether black holes and wormholes might somehow be connected. Perhaps not as the dramatic portals of fiction, but through deeper geometrical relationships hidden within spacetime. At present, no evidence demonstrates such a connection. The idea remains speculative. Yet black holes continue inspiring questions that reach well beyond astronomy itself. You continue onward. The cosmos grows even stranger. Another possibility appears on the horizon. White holes. If black holes allow matter to enter but not leave, could a reverse phenomenon exist? A region from which matter emerges but cannot enter? Mathematically, certain solutions seem to allow such objects. Physically, their existence remains uncertain. No confirmed white hole has ever been observed. No telescope has captured convincing evidence. Yet the idea persists because mathematics occasionally hints at possibilities before nature confirms or rejects them. Science progresses through this tension. Theory explores. Observation judges. Sometimes theory wins. Sometimes reality vetoes the proposal. The universe remains the final authority. You drift onward through the dark, and then you encounter one of the most important ideas in modern cosmology: cosmic inflation. To understand why inflation matters, imagine rewinding the history of the universe. Galaxies move closer together. Clusters compress. Matter becomes denser. Temperatures rise. Eventually you approach the extremely hot, dense conditions of the early universe. But certain observations create puzzles. Why does the universe appear so remarkably uniform on enormous scales? Why is space so geometrically flat? Why do distant regions look surprisingly similar despite apparently lacking time to exchange information? Inflation offers a possible answer. According to this hypothesis, the infant universe experienced an extraordinarily rapid period of expansion. A tiny region stretched to enormous size in a fraction of a second. The surprising observation is that inflation explains many features of the cosmos remarkably well. Predictions derived from inflation match numerous measurements of the cosmic microwave background, the ancient light left over from the early universe. Yet despite its successes, important questions remain. What caused inflation? What mechanism started it? What stopped it? Scientists continue investigating. The mystery is not fully solved. And hidden inside inflation lies an even bigger possibility. Perhaps our observable universe is only one region of a much larger reality. This brings you to one of the most controversial frontiers in cosmology: the idea of a multiverse. Different versions exist. Some arise from inflationary models. Others emerge from quantum theories. Others appear in mathematical frameworks attempting to unify fundamental physics. The crucial point is this: no direct observational evidence currently confirms the existence of other universes. The multiverse remains speculative, interesting, influential, but unproven. Scientists disagree about its usefulness. Some view it as a natural consequence of existing theories. Others question whether ideas beyond possible observation belong within science at all. The debate continues. And perhaps that debate itself is valuable, because it reveals how science operates at its boundaries. Not with certainty, with careful uncertainty, with competing hypotheses, with questions that may require entirely new observations to answer. The unresolved mystery here is immense. Is our universe unique, or merely one cosmic bubble among countless others? Nobody knows. For now, the answer remains hidden. You continue drifting through the darkness. The scale of the journey becomes difficult to grasp. Black holes, dark matter, dark energy, wormholes, inflation, possible multiverses. Each mystery seemed enormous when first encountered. Now they appear interconnected, threads woven through a larger tapestry, and beneath them all lies a recurring theme. The laws of physics work astonishingly well, yet they also point toward regions where understanding remains incomplete. This is one of the most beautiful aspects of science. Knowledge does not eliminate wonder. Knowledge often deepens it. The more precisely humanity measures the universe, the more sophisticated the mysteries become. A child may wonder what stars are. An astronomer may wonder what dark energy is. Both questions arise from the same source: curiosity meeting the unknown. The black hole that began this journey still occupies a special place among these puzzles, because black holes sit at the crossroads. Gravity, quantum mechanics, information, time. Perhaps solving their mysteries will illuminate many others. Or perhaps black holes are only signposts pointing toward something deeper still. The universe has not revealed its intentions. Not yet. And as your journey continues, the questions become less about objects and more about reality itself. Because eventually every cosmic mystery leads back to a handful of ancient questions. What is time? Why does anything exist? Can the universe ever fully understand itself? And those questions wait just ahead, beyond the edge of observation, where science gradually blends into philosophy and wonder. The galaxies begin to feel quieter now, not because they have stopped moving, not because the universe has become less active, but because your attention is shifting. For much of this journey, you have traveled through discoveries: black holes, gravity, dark matter, dark energy, wormholes, inflation. Each mystery occupied a particular location in space, a phenomenon, an object, a measurable effect. Now the questions become more subtle. They stop asking what exists. They begin asking what existence itself might mean. You drift between distant galaxies. Their light takes millions or billions of years to reach you. Some of the stars you see no longer exist. Some galaxies have changed dramatically since their photons began traveling. You are looking into history. In astronomy, distance and time are often the same thing. An established scientific fact is that observing distant objects allows astronomers to see the universe as it existed in the past. Light requires time to travel, so every telescope functions partly as a time machine. The farther you look, the younger the universe appears. This realization remains astonishing no matter how many times it is repeated. You never observe the cosmos exactly as it is. You observe it as it was. Every glance into space becomes a glance backward through time. But what exactly is time? That question sounds philosophical. Yet modern physics has made it surprisingly scientific. Einstein transformed our understanding by showing that time is not absolute. Different observers can experience different amounts of time. Gravity affects it. Motion affects it. The flow of time depends on circumstances. You encountered this earlier near the black hole. There, clocks disagreed. Moments stretched. The future unfolded unevenly. The black hole revealed that time behaves more like a dimension than a universal river. Yet even today, physicists do not fully understand why time seems to move in one direction. Why do you remember yesterday but not tomorrow? Why does entropy, the tendency toward disorder, appear connected to the arrow of time? Why does the future feel fundamentally different from the past? The unresolved mystery remains profound. The equations of physics often work remarkably well in both temporal directions. Yet lived experience does not. Broken cups do not spontaneously reassemble. Smoke does not return neatly to candles. Spilled cereal rarely leaps back into its bowl, particularly if gravity has become involved. The universe seems committed to preserving many mysteries. And occasionally your breakfast. You continue drifting. The stars around you feel older now. Not physically, emotionally, as though the journey has expanded your sense of scale. A human lifetime lasts decades. Civilizations survive centuries. Recorded history covers a few thousand years. Meanwhile, galaxies evolve over billions. Black holes persist for durations that dwarf entire eras of cosmic history. The universe operates across timescales almost impossible for human intuition to grasp, and yet somehow your mind can contemplate them. That fact alone is remarkable. Tiny collections of atoms, arranged into conscious beings, are capable of wondering about the age of the cosmos. The universe appears to have produced creatures able to study the universe. A strange loop. A fascinating one. This leads naturally to another question. Is consciousness part of the cosmic story in a deeper way? Science has made tremendous progress understanding the brain. Neuroscience continues uncovering mechanisms behind perception, memory, and cognition. Yet consciousness itself remains one of the most difficult subjects in modern inquiry. How subjective experience emerges from physical processes remains incompletely understood. Most scientists approach the question cautiously. Evidence remains essential. Speculation remains limited. No compelling evidence suggests consciousness influences the laws of physics in exotic ways. Yet consciousness remains extraordinary for another reason. It is the medium through which every mystery is experienced. Black holes matter because conscious beings wonder about them. The stars inspire awe because minds exist to perceive them. Without observers, the universe would still exist. But questions would not. Wonder would not. Curiosity would not. You float quietly for a while. The darkness feels peaceful. Ahead lies no destination, only reflection. And another question appears. Why does anything exist at all? Perhaps this is the oldest mystery. Older than astronomy. Older than civilization. Older than written language. Why is there something rather than nothing? Modern cosmology can describe the evolution of the observable universe with extraordinary precision. Scientists understand much about what happened after the earliest moments. But explaining why reality exists in the first place remains far more difficult. Some theories attempt answers. Quantum cosmology explores possibilities. Various models propose mechanisms. Yet no consensus solution exists. The mystery persists. And perhaps it always will. That possibility deserves consideration. Many scientific mysteries eventually yield. Planets were once mysterious. Lightning was mysterious. Stars were mysterious. Disease was mysterious. Each eventually became better understood. But not every question is guaranteed to possess an answer accessible to finite beings. The universe may contain limits, not merely technological limits, fundamental limits, questions that remain forever beyond observation, truths forever hidden behind horizons. The black hole offers a fitting symbol for this idea. An event horizon separates what can be known from what cannot be directly observed. Perhaps knowledge itself possesses horizons, boundaries beyond which certainty becomes impossible, not because science fails, because reality imposes constraints. Yet even if such limits exist, curiosity remains worthwhile, perhaps especially then. You think back to the beginning of the journey, the glowing accretion disk, the warped starlight, the silent black circle, the original question. What happens beyond the event horizon? Hours ago, it seemed like a specific scientific puzzle. Now it feels connected to something larger, a reflection of humanity's broader relationship with the unknown. We investigate, we measure, we theorize, we learn, and beyond every frontier waits another. The process never truly ends. Knowledge expands, mystery retreats, then new mysteries emerge. The cosmos remains generous in this regard. Every answer arrives carrying additional questions. You drift among ancient starlight. The galaxies glow softly around you. Time stretches across unimaginable distances. And somewhere, hidden within the darkness of black holes and the expansion of the universe and the structure of reality itself, answers may exist. Or perhaps only deeper questions. Soon you will return to the mystery that began everything. The black hole, the horizon, the secret still waiting beyond it. And there, at the edge of knowledge, the journey will finally come to rest. Not with certainty, but with wonder. The black hole returns, not because you have physically traveled back to it, but because every path through this journey eventually leads here. The shadow that appeared at the beginning now rises once more in your thoughts. Silent, patient, unanswered. Around its swirl all the mysteries you have gathered along the way. Information paradoxes, quantum fluctuations, dark matter, dark energy, cosmic inflation, questions about time, questions about existence, questions about whether reality itself can ever be fully understood. The black hole remains where all those roads seem to meet. You drift once more beside its darkness. The glowing disk circles endlessly. Warped starlight bends around its edge. The event horizon waits, as inscrutable as ever. And the original mystery still remains. What truly happens beyond that boundary? After generations of study, scientists have learned a tremendous amount. An established scientific fact is that black holes are real astrophysical objects whose existence is supported by extensive observational evidence. We have detected their gravitational influence, observed stars orbiting them, measured gravitational waves from their mergers, and even captured images of their shadows. The evidence is overwhelming. Black holes exist. Yet existence is not explanation. Knowing that something is real does not automatically reveal all of its secrets. The universe rarely makes things that easy. You gaze toward the horizon. Perhaps information is preserved somehow. Perhaps Hawking radiation carries hidden records of everything that falls inward. Perhaps spacetime possesses structures not yet understood. Perhaps quantum gravity will eventually resolve the paradox. Perhaps the singularity itself is an illusion created by incomplete mathematics. All remain possibilities. None have yet become definitive answers. The surprising observation is that the more precisely scientists investigate black holes, the more they appear connected to fundamental questions about reality itself. A collapsed star somehow became a doorway into the deepest problems of physics. That transformation is extraordinary. What began as an astronomical curiosity evolved into a challenge touching nearly every major theory we possess: gravity, quantum mechanics, thermodynamics, information, the nature of space, the nature of time. The black hole sits quietly at the center of all of them, and still it refuses to surrender its final secret. You watch distant galaxies beyond the shadow. Their light crosses billions of years before reaching your eyes. Some formed shortly after the universe itself began. Others continue evolving even now. The cosmos feels ancient, yet strangely unfinished. That feeling may be one of science's greatest gifts. The recognition that understanding is always incomplete, not because knowledge is impossible, because discovery is endless. Every generation inherits mysteries from those who came before, then leaves new mysteries for those who follow. The chain continues. You think of ancient skywatchers studying the stars. They knew nothing of black holes, nothing of galaxies, nothing of dark matter, nothing of spacetime. Yet they looked upward and wondered. Modern astronomers do the same. Only the questions have changed. The wonder remains remarkably similar. Perhaps future civilizations will solve the information paradox. Perhaps they will uncover the nature of dark matter. Perhaps they will understand why cosmic expansion accelerates. Perhaps they will discover entirely new mysteries beyond anything currently imagined. The universe seems exceptionally talented at surprising its observers. It has been doing so for billions of years. There is little reason to believe it plans to stop. The black hole remains silent. The horizon remains closed. The answers remain hidden. And somehow that feels appropriate, because complete certainty might make the cosmos smaller. Mystery gives it depth. Mystery gives it distance. Mystery gives it room to remain vast. You drift quietly beside the darkness. No alarms sound. No revelation arrives. No final curtain lifts. Only the stars remain. And perhaps that is enough. For now. The journey slows. The galaxies become softer. The black hole grows more distant. The questions linger, not demanding answers, simply existing, waiting, as they always have. And as the universe continues unfolding across incomprehensible ages, the mystery remains suspended between knowledge and ignorance, a reminder that humanity has traveled remarkably far, and that the deepest secrets still lie ahead. Now the stars begin to fade gently into the background. The pace slows further. The cosmos settles into silence, and the long night drifts toward its final moments. For a while, simply rest here. Imagine the stars scattered across the darkness. Billions upon billions of them. Some newly born. Some nearing the ends of their lives. Some accompanied by worlds no human will ever see. Their light crosses enormous distances, patiently traveling through expanding space. Around them gather galaxies, great islands of stars turning slowly through cosmic time. Spiral arms rotating over hundreds of millions of years. Clusters moving through the darkness like luminous cities adrift in an endless sea. Between those galaxies wait black holes. Some small, some gigantic, each guarding mysteries that continue challenging the best minds on Earth. Their horizons remain closed, their interiors hidden, their secrets still incomplete. And beneath everything, deeper still, quantum particles flicker within the fabric of reality. Tiny fluctuations, fields and probabilities, the microscopic foundation beneath stars, planets, galaxies, and perhaps spacetime itself. The very small and the very large remain connected in ways we do not yet fully understand. Across all of it flows cosmic time. From the first moments after the universe began, through the birth of stars and galaxies, through countless ages yet to come, time carries everything forward. Worlds, civilizations, questions, dreams. The black hole remains somewhere out there. The mystery remains somewhere out there. And perhaps that is comforting, because even after all humanity has learned, the universe still contains horizons not yet crossed, still contains questions not yet answered, still contains wonders waiting patiently in the dark. So as the stars continue shining across unimaginable distances, and galaxies continue turning through the ages, and black holes continue keeping their silent watch, you can rest knowing that the story is not finished. Not for science, not for the cosmos, not for curiosity. The deepest secrets remain hidden, and the search continues, far beyond tonight, far beyond tomorrow, far beyond the reach of any single lifetime, under the stars, among the galaxies, beside the black holes, within the quantum particles, across the vast river of cosmic time. The mystery endures, and the universe, as always, keeps watching in silence.